Hello everyone, Nadlabs here, and today we're going to be trying to solve this organic chemistry problem. So in this problem we have as you can see over here, we have 3 methyl hex 3-ene, right? Because we have 1, 2, 3, 4, 5, 6, and then we have a methyl on the third group, and then we have a double bond on the third carbon. At the moment we have the E version of it. We're going to try making the Z version as well, so we can just copy this over. In order to make the Z version, we'd have to make it on the same side. Remember the little memory device that almost all professors use, so we can just flip this around. And we can see over here that the two biggest groups are both on the same side of the molecule or across the double bond. They're both over here instead of over here. So now we have our two molecules. We can just put them side to side. And it's going to ask, and the question's asking, what happens when we have a hydroboration reaction with this. So we would have the BH3, the boron molecule. There's multiple different ones you can use. It doesn't matter. In this reaction, because we're doing a hydroboration reaction, we're going to be adding hydroxyl to the carbon with more hydrogens, or at least it's going to be anti-Markovnikov. That means that there will be an OH here. There will be an OH group, as opposed to if we did a hydration reaction, which would actually have the OH group over here, assuming that the double bond broke in both instances. But we're not doing that. We're going to be doing something like this. Let's pretend that we have our BH3 coming in, right? And as you know, it'll actually be in a syn addition, so it's added on the same side. So there's also an H over here that will be added to that carbon like that. After, so I'm just basically doing the reaction mechanism. Of course, there's like two other over here, but that's kind of unnecessary. All you have to know is that after this reaction happens, or after this BH3 is able to approach this double bond, it's able to bind to it, and it actually breaks the sp2. It actually breaks the double bond here, and it makes its own bond over here like this. So it's BH2 actually now, and there's going to be an H over here as well. And we can get rid of this double bond. The same thing happens over there. I'll get to that in a second. And for clarity, I'm just going to draw in the other hydrogen that's also here, because it's also here as well. There we go. I have the other hydrogen. So you can see that we have alkane now. But what happens is, with hydrogen peroxide, you're able to replace this BH2 with water, which we can easily just do by going like this. And now we have our molecule that's created when this reaction happens. And of course, we have to pay attention to the other version, which was with the E isomer. We added the OH to the carbon with more hydrogens over here. As you can see, this one technically had a hydrogen beforehand. If I just quickly grab it and move it away, you can see that this one has one more hydrogen than this one. This has 0, right? Because it's already connected to this carbon, this carbon, this carbon. But this carbon over here is connected to a hydrogen, carbon, and another carbon. After we use the boron and then we add the hydrogen peroxide, we'll be able to attach our water right here. Our double bond will disappear. And we'll also have another H group, or we'll have a hydrogen over here as well. If we look at these molecules right now, we can see that this OH is up here, and it's to the left, or it's to the right of this. Let's just call it an ethyl group, okay? From here to here, that's an ethyl group. We can see on this molecule over here that was originally an E isomer. We can see that the OH is to the OH is to the left of the ethyl group. This one over here. That's kind of important, because that, if we're like, of course, this is kind of a contrived example, but if we're making drugs or something, the isomer, the stereochemistry actually matters a lot. So we would have to take that into account, and this is a good example. So if I overlap these, right? If I just overlap this molecule with this one over here, we can see that a lot of it matches up. Like this back part is almost identical, right? We have the H, we have this methyl group over here, and then we have this other chain over here. It matches up, but over here, the OHs matches up, like literally the OH kind of match up, sorry. There we go. The OH match up, but you can see that it's kind of funky where the H over here is on the right, but on the original E isomer version, it's on the ethyl group is on the right, and vice versa for this one. So how can we, like, what's the mechanism for like labeling a stereoisomer? Well, it's the RNS naming system. Of course, it has a proper name like Hans Engel something something, but I don't remember that. I just know how to do it. So we're going to do that as well. So we can start off with numbering priorities. So just looking at these, we obviously know that the oxygen is going to be higher priority because it's higher atomic mass. That's just the naming convention that humans use. It's nothing special. So we have 1 over here. Then we have to compare this carbon and this carbon. What's this carbon bonded to? It's bonded to another carbon, so C, and it has 2 invisible hydrogens over here. So we can just say CHH. What's this one bonded to? Well, it's bonded to this carbon over here, and it's bonded to that carbon over there, so C, and it's another hydrogen. So this one is technically heavier. That one over there is technically heavier, so that will be 2, and then this will be 3. So we can just, if we just look at it from this angle over here, we can just draw a arrow like that. That's the direction, and looking at it from this direction, you would be so tempted to say it's R. But look at where the fourth group is. The fourth group is right at us. So that means this is the S configuration because the smallest group is towards us. It's like directly at us. If I was standing over here, if I'm standing over here, you can see that it is S because R is like this and S is like this. Taking that into account, we can just grab this and we can compare. Oh yeah, these are going the same direction. So this one's S. This molecule, the one that was originally a Z isomer, remember same side, whatever. This creates the S version for this molecule. But if we go over here and number over here, so let me just do that again. So 1, we have 1, oops, we have 1. Then this will be 2 because we can just carry all of our logic and counting. 1, 2, 3, and this is 4 obviously. But I'm just going to stand over here and draw the arrow. So we have 1, 2, 3. So it's kind of like that. 1, 2, 3, and we can see that this is R because the hydrogen's back here, right? You can see that it's at the back, and this will be R then. How about the carbon over there? Because remember, there's 2 chiral centers. I was editing the video you were just watching, and I realized I made a mistake. And the mistake I made was that when I was talking about the hydroxyl being added over here, I somehow mistakenly, like this, I put the hydrogen down here. And the question clearly stated that we did a hydroboration reaction. That means that this system or this configuration where the hydrogen is added anti to the hydroxyl or water over there and this anti addition is actually incorrect. What it should be a H up here as well, and then this one down here should have been pushed down, and this one should be pushed down like this into a sort of tetrahedral geometry, right? Because it's now sp3. This carbon over here in the center of this plus is sp3 hybridized because it has 1, 2, 3, 4 charge centers, or it has 4 bonds, so it is sp3. And over here we have a small hydrogen back here. If I could just find the icing, we have a small hydrogen over here. This hydrogen was already there when we started with the molecule and is not something we have to worry about a lot. But we want to find, if we know that this is, if we know that this one over here is either R or S, I forget, I have to do it for this one. I can quickly do it. So I know this one, this is bonded to 2 carbons, this is bonded to 1 extra carbon, so this has to be 2, this has to be 3, so this will be like this, and I can see that the hydrogen is back there, so I know I'm looking at it. So I know I'm looking at it the correct orientation. This is the R version, and now I want to figure out for the other carbon. You can do it for both molecules I drew in the like 2 minutes ago, but I will only be doing it for one of them because, and you can pause and figure out why. But the reason is because this backside remained the same throughout the reaction mechanism. It didn't change. When we look at this molecule, it'll still be the same. That's quite large. How can we go around figuring the RS of this? Well, we know what to do. We have to label each one. I can obviously see that this one is going to be it's going to have a higher priority because this carbon over here, because it's bonded to an oxygen, so this is probably 1. This has more carbons than this, so this is 2. This is 3, this is 4. So what I'm going to do is I'm going to crouch, ouch, and I'm going to look up, and then I'm going to draw, that's 2, so like that. There we go. Ow, what the hell? Okay, whatever. And now you can see that we have our arrow. So what I'm going to do is so now you can see that we have our rotation. I'm just going to grab everything, and I'm going to rotate the entire molecule so it benefits me when I'm trying to figure out how this works. So I can see it was like this, now it's like this, and what I'm going to be trying to figure out is hydrogen at the back like this, and I can see that it is definitely in an S configuration. How do I know it's S? Well, because I know the hydrogen is at the back, I can see that the 3 priority groups are all facing me, and they go into a 1 to 2 to 3, so it's like this. The R configuration is like this, and the S configuration is like this. I'm going to double check on Google. LibreText, okay, LibreText says clockwise R, counterclockwise S, okay? Don't believe me, believe chemistry LibreText, and you can see that this is definitely counterclockwise because I'm looking at I'm looking at a clock right now, and I could tell you that the clock was moving like this, and that's R, so that means this is S. This is S over here, and we can now say third carbon that used to have the double bond. That one was that one at the end of this reaction mechanism is in a S configuration. Yes, S. Boom, there we go. Thank God I re-recorded this part. That being said, I hope this VR chemistry video helped in any way, tiny bit. That would be amazing. And that's all I have to say. Goodbye. But all you have to know is that's anti-Makarov. It's an anti-Makar. It's anti-Makar. It's anti-Makar. It's anti-Makar. Makar. Makar. Makovnikov. It's anti-Makovnikov. Markovnikov. 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 Ow! That was bad. Okay, I'm gonna stop. Incorrect. So, I shall re-record that part because I would rather have a correct video than a wrong video. Okay. We can just, oops, I didn't want to delete that. In addition, the question also asks us to consider stereoisomers. Wait, what's the point of me making this video?